All right. So essentially, because we derived the speed of the shock wave using an analysis, we can only derive it by using analysis of the integral form. Finite volume is actually doing the right thing by directly discretizing the integral form. And you can actually prove using pretty much the same analysis that if you use finite volume as opposed to finite difference, the speed of the shock wave is actually going to be captured correctly. I mean, I'm not going to be doing the proof in class, but like you can, if you're interested, you can actually do it yourself. The only difference is that in finite volume, except for a exactly sharp drop, okay, the picture in finite volume is going to be a little bit more smeared out. When you have finite volume, the shock wave is probably going to be like several staircases, something like that. I think we have seen that in our previous MATLAB example, right? So if we initialize the solution again and solve this equation again, what you see is that, right, this shock wave over here is actually discretized not into exactly a discontinuity, but into a finite number of steps. Do you see that? I hope you see that through Zoom. Is it clear enough? I don't know if the video is clear enough. Maybe not. Yeah. Oh, okay. Okay, so maybe let me, if not, let me actually change the line width a little bit. Something like that. I don't know if it's enough. Yeah, okay. So line width is, so you can see here, it's actually, right, we have a finite number of steps that's approximating the shock wave. So you get a finite number of steps, and you can use the same analysis here. You have a left here, you have a right here, and no matter what the shape is, you're going to see that the speed of the shock wave, right? So after a while, this shape is going to be, it's going to be shifted to something like that, right? But this area is going to be the change in the integrated solution. And you can basically analyze that the speed of this numerical shockwave has to match the speed of the analytical shockwave. So we can prove that finite volume does the right thing in capturing the movement of the shockwave. And that's something you can never prove in finite difference. Okay, actually, if you run finite difference, you can visibly see that in a lot of situations, the speed of the shock is just totally wrong. You can find out that a shock wave that should be moving actually sits there stationarily. So finite difference is not going to be a good method if you want to resolve shock waves. Finite volume should be the method you're going to be using. All right. Okay, any questions so far?